Every few months.
Yeah, I'll be glad to regale you with my unnecessarily knowable knowledge.
Good. Gail means
Irrelevant facts that are some of the best ones to know, but absolutely not. Okay, continuity. Continuity is extremely important. Everything I say is important, but something is more important. No, continuity is really, really, really important. Okay. We need to know where a function is continuous. Technically speaking, calculus applies only to continuous functions. However, we are smart people. We will be able to make adaptations to discontinuous functions and apply them as necessary. Now, definition. A function f is continuous at point C if these three things are true. These conditions must be met for a function to be continuous. 1, f of c is defined. 2, the limit as x approaches point C of f of x exists. And 3, the limit and the function have the same value at that point. Okay? So this is continuous at a particular point C. A function is continuous at a particular point C if it is defined at that point, if there's a limit at that point, and the limit and the function have the same value at that point. Okay? You have to have all three of those conditions met. If all three of those conditions are not met, it is not continuous at that point. Okay? A function is continuous on an open interval from A to B if it is continuous at every point between A and B. Open interval, does that mean the endpoints are included or not? Bless you. No, the endpoints are not included. In the open interval, it's very important. It is continuous on an open interval if it's continuous every point between beginning and end. Every point must exist. Every point must have a limit. And at every point, the limit and the function have the same value. Okay. These definitions are important. These definitions come up as questions. If you're asked, is a function continuous? If I have a test question that says, is this function continuous at this point? You need to say, this is true, and this is true. You must state all three of those things are true. You cannot just say yes. You have to state specifically, yes, this part, therefore it is. It must meet all the conditions, or not at all. Okay. Questions about what it defines to be continuous. At a point, at all points. Okay. Now, a function f of x is continuous at a left endpoint or a right endpoint if, so at a left endpoint. So if I have, here's point A, here's point B. It is continuous at A if the limit as I approach A from the right is equal to f of A. So at an endpoint, because can I have a two-sided limit at an endpoint? No, I can't have a two-sided limit at an endpoint because I can only come at it from one direction. The other direction doesn't exist, so I can't come at it from the other direction. So I have to have a definition that says, hey, I can be continuous at a particular endpoint if my limit going towards that endpoint and the endpoint have the same value. Same thing from the other direction. If my limit from the left of B is equal to f of B, it is continuous at the end point. And yes, you have to define these particular values and say, well, it's continuous, because that would not meet the definition of the previous one. The limit at B itself does not exist. Technically speaking, the limit of B does not exist because My right and left-hand limit do not equal each other. My left-hand limit is one value, my right-hand limit does not exist. How can I have something that exists equal something that does not exist? They don't. So technically speaking, it can't be continuous by the previous definition because the limit comes from both directions. But an endpoint can only come from one direction, so we have to say, okay, it's all right if it's an endpoint we come from one direction only. Or we come from the other direction for an endpoint on the other end. If you don't define it, it doesn't work. Okay. And when we're talking about any point C, if I have some point C here in the middle, as long as the limit and the point exist, it's continuous. This curve would be continuous everywhere from A to B, including A and B. Because it's continuous between all the points. Visually, you can look at it and see that.
So if the point was like,
If there was a hole, we got a problem. And we'll talk about discontinuities, specifically discontinuities. Because there are different types of discontinuities. You have to understand which ones are which. Okay? They actually name the discontinuities. Okay, so let's take a look at this one here. So, take a moment, answer the questions. Limit to, as I approach 1 from the right, from the left, 1, f of 1, is it continuous, yes or no? Okay. So the limit as x approaches 1 from the left-hand side is 1. The limit as it approaches 1 from the right-hand side is 1, which means the limit as it approaches 1 is 1. So I can't have the limit if I don't have these first two equal to each other. That's an important distinction. Does the limit exist? Yes or no? Yeah, it exists because these two are the same. What is f of 1? 1. Is it continuous? Yeah. This is true. This is true. These two are equal to each other. Yes, I have 3 conditions. All conditions have been met. And I must meet all conditions, yes.
If the first two aren't the same.
If these two are not the same, this does not exist, you're done. Because you have to have a limit. If you don't have a limit, it's done. These two are not the same, you don't have a limit, it's not continuous no matter what.
And then do the bottom two have to be the same?
Well, this would be, these, you have to have, okay, this has to be true by itself. This has to be true by itself. And these two have to be equal. Those are the 3 conditions. Okay? Okay. Do it again. Okay. So the limit as I approach 1 from the left is 0. The limit as I approach 1 from the right is 0. So the limit as I approach 1 is 0. What is f of 1? 1. Is it continuous? No. The limit, and here let me do this. Let's see if I can get this. The limit as x approaches 1 of f of x does not equal f of 1. That's why it's not true. Now, this is a removable discontinuity. This is a removable discontinuity. If you have a hole in your graph and it's just missing that one spot, it is called a removable discontinuity. I've removed that point. Now, your removable discontinuities can either be just this without the extra point, or with the extra point like this one does. So I can also have them be, if it were just that, if there was no value here, it would still be a removable discontinuity. So I got a line, I pulled the hole out of it, I removed it, that's a removable discontinuity. Okay, do this one. Some interesting discussions I hear going on, and there's some things that we need to clarify on this. So first of all, as it stands right now, the limit as I approach 0 from the left-hand side is -1. As I approach 0 from the right-hand side, +1. The limit does not exist, so no. It is not continuous. Doesn't matter the rest of it. If I don't meet one of them, the limit does not exist. It's not continuous, period. Okay. Now, what is f of 0? Does not exist. However, if I had filled in one of the points, it would be that point. If I had filled in both points, this no longer qualifies for being continuous because what? It's not a function. And the definition of continuity is a function is continuous. If it's not a function, we can't apply the definition of continuity to it. Okay? Now, this is a jump discontinuity. If you have to go to one place and go to another and there's a gap other than the little hole, this is a jump discontinuity. If you have a left and right hand limits and they're not equal to each other, that is a jump discontinuity. Because if the little ant was running along, how'd they get from one side to the other? They'd have to jump. I don't know. That's a good reason as any.
That's a very
Okay. Where is this function discontinuous? Yeah, it's at the asymptotes. Okay, so it would be at that's what? That's pi over 2? Or is it pi? Tangent is sine over cosine. Cosine is 0. Cosine 0, pi over 2, 3 pi over 2, 4 pi, and in the negative direction, right? Where the cosine is 0, which is any odd pi over 2. Positive or negative, odd pi over 2. Cosine is negative. So that's where it doesn't exist. This is called a infinite discontinuity. This happens when it's discontinuous due to an asymptote that is called an infinite discontinuity. Yes. You will need to know this. You will be asked to identify what type of discontinuity.
so this is
an infinite one. It's not infinite because it has an infinite number of discontinuities. If we were just talking about one portion of this, it's an infinite discontinuity because of the asymptote.
okay.
Not because there's a lot of them, but because it has an asymptote. It's a discontinuity because it has an asymptote, and because it's an asymptote, that is an infinite one. It has several, let me be clear, it has several infinite discontinuities. Does that make sense? Does that help clarify it? It has several infinite discontinuities. Because the limit goes towards infinity as we get to that point, that's what makes an infinite discontinuity. Okay? Does that help clarify it up? It's not how many discontinuities, it's what kind of discontinuity. There is an infinite number of infinite discontinuities in the entire graph of real numbers of the tangent. And then this one. Okay. Yeah. Now this is a gnarly one. I like this one. Okay. Where would you looking at the equation, because it's really hard to tell from the graph, but where would you pick from the equation where the discontinuity would be? It's 0. And it is discontinuous at 0. This is called an oscillating discontinuity. You don't see them a whole lot, but the idea is it gets in there and it's doing so much and going up and down and oscillating so much that you can't tell what's going on in the middle. That's an oscillating discontinuity. Don't see this a whole lot. Basically, this is where it happens. Trig functions where you have a 0 in the denominator of whatever you're taking the trig function of. That's where you see them. Okay. And why is it important to know continuities? Because one of the definitions when we get to the derivative in chapter 3, in order for the derivative to exist, one of the conditions for the derivative to exist is for the function to be continuous. If the function is not continuous at a particular point, you cannot take the derivative. at that point. Continuity is extremely important because the basic concept, the basic thing we work with, the big overall writing concept of calculus is derivatives. And you cannot take the derivative of a function where it is discontinuous. Okay? That's really one of the big reasons why this has to be true. Okay. If f and x and g of x are continuous at C for every point in the real numbers. So that should be B is an element of the real numbers. C is the element of the real numbers, not B is an element. That should be a C here. So if I have a function f that is continuous everywhere, and a function g that is continuous everywhere, it must be continuous everywhere for both of them. Then, oh no, sorry, that is supposed to be B. And B is an element of the real numbers. A constant times a function is continuous. Two functions added together are continuous. Two functions subtracted are continuous. Two functions multiplied are continuous. And two functions divided are continuous as long as the denominator is not 0 or one of those points. Okay? They have to be continuous. And yeah, that is B is an element of the real numbers. So, and we don't work with imaginary numbers in this class. Calculus of complex numbers, we don't do. There's not a lot of calculus of complex numbers anyways. Yes.
What does that mean? Element?
It's a B. B is an element of the real numbers. That means B is in this is within the set. Yeah, if you want to have something interesting to look at, open up the first inside pages or the last inside pages of a logic book. It is filled with nothing but symbols and what they stand for. Backwards letters, upside down letters, goofy crap like that. It's amazing what you can write strictly using logic symbols. I had a student do that to me one time. They wrote me, it was like a line that's like, 7 or 8 things long. Then they wrote out in a paragraph what that meant. Yeah. She went on to go to Stanford and get a degree in biology to become a vet. That was probably one of the more fun students telling me that they got in. She comes to me, and she's literally shaking with excitement. I got in! I got in! Literally shaking with excitement because she had just found out that she'd gotten accepted to Stanford. So that was really kind of cool. Okay. I like this one.
Yeah.
Okay, example, find A and B so that f of x is everywhere continuous. It's actually not that hard to do. Hey, so for every value of x larger than 2, f of x is defined by 1/8 ax cubed minus bx plus 3. At 2, it's defined as 2x minus 1/2 x squared. At every point less than 2, it's 1/4 ax cubed minus bx minus 5. In order for it to be continuous at 2, in order for it to be continuous everywhere, which means basically at 2 is the only place we have to worry about. Why do we only have to worry about 2? Because that's a polynomial, and that's a polynomial, and polynomials are continuous everywhere. You will love polynomials because they fit almost every single thing we ever want to talk about without having to worry about it. However, this approaches 2 from the right, approaching 2 from the left. And what do they have to do? They have to go the same number, and that number has to be what this is at 2. So what do you have to do? Plug in 2, plug in 2, plug in 2. Set this equal to that, set this equal to that. Solve for A, solve for B. You got a system of equations. Go for it. Okay. So, let's plug in 2. Put in 2 in the first one. 2 cubed is 8, so I get A minus 2B plus 3. Plug 2 in here, that's 4 minus 2. So I get 2 for that. I'm just going to write it over here. I plug 2 into this one. I get 8, 1/4 of 8. So I get 2A, and that's minus 2B minus 5. And those need to both, in order for it to be true, these two need to be equal, and they need to be equal to 2. That needs to be true. Now, that's a nice system of equations. So if I take the bottom one here, move the 5 over, 2A minus 2B is equal to 7. Take the 3, move it over. A minus 2B is equal to -1. And then subtract. 2A minus A is 1A. -2B minus -2B, no more B's. 7 minus -1 is 8. A is 8. Okay, take 8, plug it in for A in either equation. I would put it in here. 8 minus 2B is equal to -1. -2B is equal to -9. B equals 9/2. By the way, when you get your graphing calculators, your graphing calculators will do that for you.
Oh, yeah.
Your graphing calculators will do that for you. When you get your graphing calculators, learn how to have your calculator do it for you. It's not that you can't do it by hand, and you do need to know how to do it by hand. This is not an unrealistic AP multiple choice question. I've seen ones like this, maybe not quite this complicated, but I've seen ones like this where you have to do this kind of thing and solve for A or solve for B under certain circumstances. 99% of the time, they will be on the non-calculator portion of the AP exam.
Wait, so since they didn't equal, but you're saying they had to equal, both of them not equal to, so they went in.
Yes.
So could you shut them down to each other?
What?
Could you shut them down to each other? That way?
Yeah, but to be continuous, they don't have to be equal to each other. They have to be equal to the function at that point as well. Remember, definition has to be all three things for that.
All right.
Function has to exist, limit has to exist, and the limit and function have to be the same value. Okay. Find the extended piecewise function that will make the following continuous at the given value. It is discontinuous at x equals 1 because it is undefined at x equals 1. Is this an infinite discontinuity, a jump discontinuity, a removable discontinuity? It's obviously not an oscillating one. It's removable because if I simplify it down, it's no longer there. Okay, but there's a hole in it. If you were to graph it, because if you take f of x, x minus 1, x plus 1 over x minus 1, those cancel, it's equal to x plus 1. The graph of x plus 1 is the same as this graph, except this one has a hole at 1. My piecewise function, f of x equals, that's not a crappy bracket, get over it, x squared minus 1 over x minus 1 when x does not equal 1, because at 1 I got a problem. Okay? But when x equals 1, what do I need to have? What value of y will fill in my hole? Put in 1 for x, I get 2. Because remember, this and that are exactly the same, except for that has a hole where x equals 1. Where do I fill in the hole? I fill in the hole by going back to that one. When x equals 1, y equals 2. That filled in my hole. I no longer have a removable discontinuity. I came along with a shovel and I filled in the hole. Okay, that's how you do that. Yeah, fix it. Question. Okay. Shh. Intermediate value theorem. Your calculators work. The solvers on your calculators work by the intermediate value theorem. The intermediate value theorem is extremely important. If f is continuous on a function from a to b, so it is a closed interval, so I go from point A to point B, all the x's, f of a exists everywhere from f exists everywhere from here to here. Okay. And m is an element of the real numbers. And m is between f of a and f of b. So m is my y value. So I have 2 points. I have a and b. I have corresponding y coordinates with them. So I have the coordinate a, f of a, the coordinate b, f of b. And they are connected by a continuous line. Yes.
Well, can you explain what the M?
That means it's m is an element of R. M is an element of the real numbers. So I have point m that is the element of the real numbers.
What do you mean by it's the element of?
It's a real number. It's not fake. It's real. It's not imaginary like my friends. I said my friends, not his. Okay. So then there exists a point C. That's what the backwards capital E is. There exists. Told you. Math language is funny. There exists a point C that is an element of A to B. In other words, C is between A and B, including A and B, such that f of C equals that point in between. So if we look at the graph, here's what it's saying. I have a function that goes from here to here and exists everywhere in between. And I have the point A, f of A, and the point B, f of B. Okay, those are my xy coordinates. So I have f of A and f of B are here. So there is if there is a y value between here, has a corresponding x value between here and here. At least one. Maybe more than one. But I have, here's my y for the A and here's my y for the B. For every y value between those 2 points, there's a corresponding x value between those 2 points. That's what it says. If I'm going from here to here, if there's a y coordinate, I can find a corresponding x coordinate. Why is this important? Okay, let's say I'm trying to solve a problem, and this is how your calculator works. So you tell your calculator to solve a particular equation, blah, 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 equals 0. So here's what it does. Your calculator, at least this is what they used to do, I think they still do it, the algorithms may have changed. What your calculator would do is say, okay, I'm going to plug in a number here. And let's say I put in 5 for x, and I get 3. Okay. Actually, what it do is it always plugs it, start at 0. I'm looking for where this equation is equal to 0. Plug in 0 for x. Do I get 0? No. If I don't get 0, then I start trying numbers larger and smaller, larger and smaller. So let's say I plug in 0 for x, and I get 3. 3 is positive, but I'm looking for 0. What we'll do is we'll put in something a little bigger, a little smaller, 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 until it gets a negative number. what happens between a positive number and a negative number? 0. So then it says, ooh, I went from positive to negative, so that means I can go to where I went to positive to negative. I can move a little closer to where that negative was, and I start doing that again, and I start narrowing the gap, narrowing the gap, narrowing the gap, narrowing the gap, until I get where it's equal to 0. So I know if it's continuous and I go from positive to negative, if I go from above the x-axis to below the x-axis, somewhere it's got to cross it. Where is that point at? That's what this says. If my y value is above and I have another y value at the other endpoints below, somewhere, at least once, it's got to cross. At least once it's got to cross the x-axis. That's what the intermediate value theorem says. It says, if I go from here to here, it's got to be a point, a place that I can find where it is in between those two. It has to exist. The important part of this, it has to be continuous. If it's not continuous, the intermediate value theorem does not apply. Okay, so here's what they're saying. Is there a place between 0 and 5 such that f of that point, is there a point C between 0 and 5? Where the function equal to 11, where f of C is equal to 11. Is there a point between them? So how do I test this? Well, find the endpoints. What's f of 0? -1. What is f of 5? What is it? 29. Is 11 between -1 and 29?
Yes.
Yeah. So, f of x is continuous. Is f of x continuous? It's a polynomial. It exists everywhere, and the limit exists everywhere, and the limit of the function are the same. Polynomials, like I said, polynomials are sweet. Polynomials are continuous everywhere. They're nice. You don't have to worry about a whole lot. All polynomials are continuous. So f of x is continuous. Uh, 11 is between f of 0 and f of 5. It's between those two. I've met my conditions. Therefore, there is a C such that, okay, actually I should put this on. There is a C between 0 and 5. I'm going to clean this up. No. Therefore, there is a C between 0 and 5 such that f of C equals 11. There is a point. Do I know what that point is? No. I don't care. But I know it exists. So if I really do want to know what it is, I can go out and find it. But I don't care. All I'm caring is, does it actually exist or not? That's what the intermediate value theorem says. I go from here to here. 11 happens between -1 and 29. Because I have this y value and this y value, and what I'm looking for is in between. It happens. There's an x coordinate that will spit that out of the function. Intermediate value theorem says it will work. There is a solution. There is an answer. Okay? Any questions? I do believe. Oh, I like this one. We're going to just set it up because I want to give you a little bit of time for your quiz. So you don't really need a lot if you know what you're doing. If you don't, oh well. Okay, is there a number that's exactly 1 less than its cube? Is there an x that is 1 less than its cube? Is there a number that is exactly 1 less than its cube? Here's what you need to do. If I rearrange it, is there a solution to this problem? I can prove by the intermediate value that yes, it's true. All I have to do is do 2 things. 1, prove that that's continuous. Is that continuous? Yeah. 2, find a number where x cubed minus x plus 1 is positive, and another number where x cubed minus x plus 1 minus 1 is negative. Because what happens between positive and negative? 0. If it's continuous and I go from a positive y value to a negative y value, or the other way around, somewhere in between, it's got to hit 0. Intermediate value theorem will prove there's an answer. It won't give it to me, but it'll prove there's an answer. Let your calculator do the solution. Because you can't factor it. It's not factorable to solve that way. You got to do it other ways. Okay, but the intermediate value theorem lets you say, yes, there is a solution. And you want to do that before you go any farther. Okay?